research associate here over the last 6 months or so. So Sushil's thesis is in a different topic. When Sushil came here, we were inspired by a lecture that Rieffel gave, and we kind of thought we'll learn something. It was not clear whether we'll be able to produce anything at all. I'm sure Sushil learned more than I did, and in the end, we managed to write something. Sushil will give an overview starting from the classical stuff, and perhaps at the end also will mention our small contribution. So Sushil, on sequence of operator algebras converging to the sphere, but the converging to the sphere means converging to the continuous function. Sushil.
I would like Professor Tirthankar for giving this opportunity. So today we'll see this work of ours. The article can be is available on the archive. So we'll talk about a sequence of operator algebra converging to odd sphere, as Professor Tirthankar said, converging to the space of continuous functions on odd sphere in something called quantum Gromov-Hausdorff distance. So all these terms we'll see during the talk. What are these? So this is basically an overview of what we are going to talk. We'll start with the classical case. What was basic motivation for this? That start from the Lipschitz functions and something called Mons-Kantorowicz metric. Then we'll go to the compact quantum metric spaces, and as the title says, the quantum Gromov-Hausdorff distance. And in the last section, we'll talk about the sequence of operator algebra that will converge to the odd space. So let me start with the very basic definitions of Lipschitz functions. Throughout the talk, we'll take Xt to be a compact metric space. So for a continuous function, we can define this quantity, which is supremum of mod fx minus fy upon dxy. And this quantity is related to Lipschitz function. A function is Lipschitz if and only if this quantity is finite. And the space of Lipschitz function is a vector space under our usual coordinate wise addition and coordinate wise multiplication and the scalar multiplication. It's clear that this is actually a semi-norm. It might not be norm because it's clear that if f is a constant function, that this quantity will be 0, and it's actually if and only. So in some sense, we can quotient out with this and make a norm space. For example, if we just fix a point and consider this modified space of Lipschitz function, which vanishes at that point, then this makes it a norm space with the quantity we defined on the last page, which was just the lowest Lipschitz bound, what we call usually. It's just not a norm space. It's actually, in fact, a Banach space. So I'll give you an overview how we prove it's a Banach space. Let's see this inequality that here the infinity norm is the sup norm. So if we take the sup norm, this inequality, we can just subtract the fx naught and we can add mod fx naught. But the first quantity, if we look at it, the norm of f minus fx naught, the sup norm of this is basically the fx minus fx naught, where x is in x, but being a Lipschitz function, this is less than equal to the Lipschitz bound and the distance between x and x naught. In the supremum, we are varying the x, so we want it something independent of x, but this is always less than equal to the diameter of x. And because we are over a compact space, so diameter of x is a finite quantity. So this is less than equal to the norm f diameter of x. So that is our next inequality. But if you look at now, this implies that if we have a Cauchy sequence in the lip of x naught with this lip norm, that will imply the sequence is also Cauchy in our infinity norm. So this gives us a candidate because we know that the space of continuous functions with the infinity norm is a complete metric space. So using the completeness, we'll get a limit in Cx, and the proof will be complete if we just prove it's a Lipschitz function. And the proof goes by our usual technique of epsilon by 3 argument types technique. So this quantity, which seems which is very classical. We must have seen this in BSc while doing the matrix spaces. So this gives us a Banach space. Today we'll see it actually gives us much more. So let me, using this, let me define a norm on the space of complex radon measures. We know the space of complex radon measure is, if we take our usual total variation as a norm, then it's nothing but isomorphic to dual of Cx. So it implies that the variation norm is nothing but the supremum of integral of f d mu, and the f will vary over the unit ball in the Cx with the infinity norm. So let's change the definition, because now we have a very different kind of norm, which is the Lipschitz norm. So let's define a new norm, which is called Mons-Kentrovich norm. Is the same definition, but instead of taking the unit ball in infinity norm, we are taking the unit ball in the Lipschitz norm. So we are varying f over the functions which are of Lipschitz norm less than equal to 1. As I wrote, it's a norm, but let's see it, why it is a norm. It's clear it's a functional which is a semi-norm. The only thing we need to prove that if the Mons-Kentrovich norm is 0, then the mu should be 0. We are over the complex radon measure, so it suffices to prove only that mu of k equal to 0 for all complex set k. Now the proof is as similar we do in the case of if we had the infinity norm. So we need something called a Eurasian type lemma for the Lipschitz function. We should state basically that if you have a compact set contained in an open set U, then we should be able to find a Lipschitz function which is basically sitting between the characteristic function of k and the characteristic function of U. And finding this Lipschitz function is very easy because we are over a matrix space, and this is a kind of Lipschitz function we can get. It's a usual. It's simple calculation to prove its Lipschitz functions with this bound on the Lipschitz norm. So just using this Eurasian type lemma, we prove that it's a norm. So we have got a norm on Mx, but this is some interesting norm because just knowing this Mons-Kentrovich norm, and if we know that we are given the Cx continuous functions on a compact matrix space, we don't know what is the metric in the beginning, but we know this norm, then we can actually recover the metric. How to do it? Because given any 2 points, we know there are Dirac delta function concentrated on those 2 points. Let's see what is the Mons-Kentrovich norm of those. That is nothing but the distance between x and y. So let's start with the proof of this. So if we take any function whose Lipschitz norm is less than equal to 1, then what will be the integral of f d of del x minus del y? By definition, it is nothing but fx minus fy, which is less than equal to the dxy because norm fl is less than equal to 1. So by taking the supremum, we get that the Mons-Kentrovich norm is less than equal to the dxy. Now we have to prove the other side inequality. Let us consider this function on the x. This is a Lipschitz function because it's just a triangle inequality. That it's a Lipschitz function. So using this, if let's calculate the Mons-Kentrovich norm should be the greater than equal to the integral of g d del x minus del y, which by definition is gx minus gy. What is gx? It's the distance of x from x, which should be 0. What is gy? It's the distance of x from y, so it's equal to the dxy. So it proved the other side inequality also, and we got that the Mons-Kentrovich norm is just the dxy. So how it is useful? Let's just see. As I mentioned in the last slide, although it was not written, but I spoke it, that assume you are given Cx, and we know the Lipschitz norm, which basically gives us the Mons-Kentrovich norm. So with this space, I can take the dual, which will give me Mx. The space of complex radon measures. It's isomorphic to the dual of Mx. Oh no, sorry. I mean, we already know it's infinity norm with the Cx with the infinity norm. And take the dual. So we know, Okay, whenever I say Cx, it means we know Cx with the, whenever we say we know Cx, it means we know Cx with the infinity norm. Basically, it's a Cx means we know the commutative C star algebra. So I'm taking the dual with respect to that. What are the extreme point of these? They are nothing but the scalar multiple of Dirac delta functions only. And as we saw in the last slide, knowing that extreme points, which are just calculated by the usual definitions, we can find the, we can recover the space and the metric. One thing is, in the extreme point of closed unit ball, there are also scalar multiple of Dirac measures. But if we just restrict to the space of probability measures, the extreme points are exactly the Dirac measures. So this is some kind of analogy which we'll see in good detail a few slides later. So this we saw in, but before that, let me show that let us see that this norm is in fact much useful. It in fact gives us, so the Px will be my notation for the space of the probability measures. So we know that there is a weak star topology on this. Now my question is this topology metrizable? So we know that if we have any norm space which is infinite dimensional, then the Y star dual of this with the weak star topology can never be metrizable. But the thing is, Px is not the dual of Cx. It's much smaller space. And what we are going to prove that it's actually metrizable, and the metrizable, and it's metrizable with respect to the Mons-Kantrovich norm. Not just metrizable, in fact, metric comes from a norm also.
Yeah, so in the earlier part, I think, let me summarize what you were trying to say, that the distance on the metric space X can be recovered in a roundabout way by looking at the extreme points of the dual of Cx in the infinity norm.
Right.
And then considering those extreme points in the metric induced by the leap norm.
Right.
This is the motivation which will be used later.
Yeah, and we'll see it again. The same thing we'll see again. So I'll try to be more precise at that time again. So, okay, so we are going to prove that the space of the probability measure with the weak star topology is actually metrizable with respect to this Mons-Kantrovich norm. So let's see the statement. In the statement, I have written that if we have a sequence of the complex radon measure with the variation norm to be less than equal to 1, and there is a measure mu whose variation norm is also less than equal to 1. Just note that for the probability measure, the variation norms are equal to 1. So they already satisfy this condition. Then our claim is that the mu k converges to mk if and only if mu k converges to mu in the weak star topology. And a priori, I could say why this less than equal to 1 condition on all mu k and mu are compulsory, because we know that the mx with the weak star topology, this is not metrizable for sure. So there has to be some condition on the sequence, and there has to be some condition on the limit, and it comes that if they are of same bound, then it works. Sorry?
Side, if Y is infinite dimensional, if Y is separable, the unit ball is Y star. Unit ball Y star is metrizable with respect to the weak star ball.
Not always. It's only weakly compact.
So Y is separable.
Infinite dimensional, then also it will not be in general.
So compact are those
In fact,
topology is generated by countable set.
Yeah, it would be generated by a. No, it will be given by a countable semi-norms, the topology, but it will not. It can't be given by single norm.
So if you have
For the set, okay.
yeah, so compact,
No, even if we have separable, okay, we can't induce it by countable then also.
Yes, in the
Yeah.
absence of countability, it won't.
In case of separable also we can't. In fact, the result is that it is metrizable if and only if y is finite dimensional.
that is the whole space right now. We're talking about the unit ball, because
Right.
those probability measures are sitting inside the unit.
Okay, so for the unit ball,
So in your case, it will be metrizable, but I don't know what the metric is, right? So I think your point is that the MK norm.
okay, about
metric. That's okay, go ahead.
yeah, so but if you are saying that for separable it holds, at least in our case we are taking any CX. X is any compact metric space. So yeah, so I have to see about, so this result I know that the Y star will not be metrizable, but about the unit ball I have to just see. Right.
Here,
Here-
the abstract theorem which tells you it is metrizable, doesn't it? You can probably write down some metric, but you may not get something explicit. Like.
Yeah, okay. So at least the theorem is saying that this weak star topology is coming from this particular metric, which is the given by the Mons-Contrevich now. So
What is metrizable, but the metric is pretty abstract. Whenever you have a countable number of seminomes, you can write down an appropriate sum to make the metric, but yeah, it's pretty abstract here. So
here we are specifying a very particular metric here. So yeah, so I'll come to the proof of the theorem. So let us assume the sequence converges to mu in the Mons-Contrevich now. We have to prove it converges in the weak star topology, which I basically need to prove that the integral of f d mu k equal to integral of f d mu for all f in Cx. But we know the Lipschitz functions are dense in Cx with the infinity now. So it suffices to prove that it holds for all f in for all Lipschitz functions. So let f be Lipschitz function be fixed. Now we know that mu k converges to mu in mk. So by the definition for every epsilon there is a k naught such that k greater than equal to k naught, then the norm of the mu k minus mu, which is the supremum of integral g d k minus mu, and the g of Lipschitz constant less than equal to 1. This can be made smaller than epsilon, and I'm also dividing it by a constant, which is the Lipschitz norm of f. Now any questions? Okay. Now given the f, if I take f upon the norm fl, it's of Lipschitz constant 1. So if I put it to g equal to the f upon norm fl, it basically implies that the mod integral f d mu k minus mu is less than equal to epsilon, which basically implies that the integral of f d mu k equal to f integral of f d mu. So the convergence in mk implies the convergence in weak star topology. Let's prove the other way around. So we want to prove that if mu k converges to mu in weak star topology, then mu k converges to mu in the Mons-Contrevich norm also. So I'm going to slightly modify the norm, and we are going to prove that mu k converges to mu in weak star, then mu k converges to mu in mk tilde, which is equivalent norm. The definition is similar. So in the definition of mk, we were taking f with the Lipschitz norm less than equal to 1. Here I'm taking the maximum of the Lipschitz norm, and the infinity norm should be less than equal to 1. Using the compactness of x and basic inequality, it's easy to prove it's equivalent to the mk. So if we prove that mu k converges to mu in mk tilde, we'll be done. Why I'm modifying it? Because I want to use some standard result and it will become very easy. So let's come to the proof of this. So assume it is not true, which basically means there is a sequence which converges to mu in the weak star topology, but it does not converge to mu in the mk tilde. Now, if necessary, we can pass to a subsequence and assume that mu k converges to mu in the weak star, and the norm of mu k minus mu is greater than sum epsilon. Now, using the definition of mu k minus mu, which is written above, for every k we can find a fk such that the integral of fk d mu k minus mu is greater than epsilon, and norm of f is less than equal to 1, where it's modified norm. Basically, the Lipschitz norm and the infinity norm is less than equal to 1. Okay, now let me come to why I took the maximum of this. The idea is because of Algebras theorem, this unit ball is relatively compact in Cx. To apply the Algebras theorem, we have to prove it's equicontinuous and the bounded. The equicontinuity comes because the Lipschitz norm is less than equal to 1, and the boundedness comes because the infinity norm is less than equal to 1. So, because of the relative compactness, there will be a sequence, subsequence, which will converge to some function in Cx. Now, combining all these data, we will get a contradiction now. We have not used till now where mu k was converging to mu in weak star. Just apply it on f. So the integral of f d mu k minus mu is going to 0. So now let's see, integral of fk with d mu k minus mu was greater than epsilon. I can add f here and subtract f. Now the first quantity is going to 0 because of the weak start compactness. For the second quantity, it's less than equal to the infinity norm and the variation norm. We know the infinity norm is also going to 0 of fki. The only problem is what about the mu k minus mu? If there is no bound on mu k and mu, it can also vary in arbitrary way. But in our assumption, we had taken that both were bounded by 1. So it converges to 0. Now the right hand side is going to 0, but the left hand side was it says that these numbers were greater than epsilon, which is a contradiction. So what we have proved that if we have the space of probability measures with the weak star topology, then it's materializable in our Monch-Contrevich norm. So now let me summarize the thing. So we were given a compact matrix space. There was a dense subspace, which was the space of Lipschitz functions. There was a seminorm L defined on Lx. The seminorm was such that L of f was 0 if and only if f is a constant function. Let me take one more thing, that L of f bar is equal to L of f. F bar is just the conjugate of f. It's very easy to say the Lipschitz norm will be the same. The most important part was the topology on the Px was coming from this particular metric, which was the supremum of mu k, mu f, where the by definition so mu f I'm denoting mu f is the notation for the integral of f with respect to mu. So mu f minus mu f and the LF is less than equal to 1. The topology generated by this coincide with the weak star topology. So this we have proved till now. The condition, the second condition, as I said, I have not used anywhere before that. But we are taking it because of some technical reason, which I'll mention when we'll come to the compact quantum matrix space. And it will give us flexibility also. And why I used all these mu f notation and all these? Because what are Cx with the infinity norm? So we'll come to these in next section on the compact quantum matrix space, but I want to give an overview basically here. So Cx with the infinity norm, they are what are called commutative C star algebra. And the space of probability measures, there is an analogous of space of probability measures on the any commutative C star algebra, what is called states. So if you are not aware of these terms, don't worry, we'll come back to these in the next slide. We'll define all these terms. But this is a general idea from the theory of the C star algebra, that if we have a commutative C star algebra, then it's isomorphic to Cx. Whatever is the isomorphism in the category of the commutative C star algebras. So this was proved by Gelfand and Neyman. So what they proved, basically, let me write down this notation. So if C is a category for the category of compact topological space, and A is a category of the commutative C star algebra, then Gelfand and Nemeth proved that these two are equivalent. Equivalent basically means from this category to this, there is a from this category to this, there is a contravariant function which is basically taking the continuous function denoted by C. The other way around, there is a contravariant functor which is given by something called max, called basically taking the maximal ideas. And these two functors are adjoint, form a what is called adjoint pair. So in this way, we are taking here commutative C star algebra. Then people go in the non-commutative C star algebra and they talk about, okay, non-commutative C star algebra can be seen as the non-commutative versions of what is called topological spacing. But what we have seen that if we have Cx with the infinity norm and there is a semi-norm also given, which was rho L, then they stores the same data as the compact matrix spaces. So why not use this semi-norm which was on the last slide with these conditions and use this as a way to motivate to define a non-commutative version of the compact matrix spacing. So at the moment using the Gelfand-Nemeth, we only have a non-commutative versions of compact topological spacing. This might be a way to find a non-commutative analog of compact matrix spaces, and this was a motivation of Rieffel to define what is called compact quantum matrix spacing. So as promised, let me start with the definition of C star algebra. It's a algebra with a unit, and there is a norm. So it's not just complete matrix space, it's a complete norm space. And there is a operation star, which is from A to A. It works just like adjoint in the matrices. Basically, A double star should be A, B star should be B star, A star, and A plus alpha B star should be the A star plus alpha bar B star. The norm satisfies what is called submultiplicative condition. Because we have defined a star operation, there should be some compatibility between the norm and star. It's given by what is called the C star condition and the norm of A star A equal to the norm of A square. The basic example being the very first example is the Cx, the continuous functions on a compact topological space. Then the space of matrices, or in general, the bounded operators on a Hilbert space. Now, let me come to what are states. In a C star algebra, a element is called positive if it is of form B star B. A functional is called positive, it takes positive elements to the non-negative real number. And a functional is called state if it is positive and takes 1 to 1. The interest, so we know in the Cx, with the infinity norm, the space of probability measures with the weak star topology is compact. The same is true for the state space also. So if we take the collection of all states with respect to a unital C star algebra, it is a weak star compact subset. And the examples are, as we see, the Cx should be the probability measures. And for the MLC, it should be what are called density matrices. Density matrix is a positive semi-definite matrix with the trace to be 1. Now let me come to the definition of compact quantum matrix space, which is motivated by our classical example. So instead of the Cx, we'll start with a unital C star algebra. There will be a semi-norm defined on a dense subset of A. And it will be called a Lip norm if it satisfies 3 conditions. The first one is L of A will be 0 if and only if A is scalar multiple of unit. L of A star should be L of A for all A in A. The topology on the state space, which comes from the metric. Now you can see why I was taking mu. The expression is similar as we had in the case of Cx. Rho L of mu nu, which is supremo of mu A minus mu A, LA less than equal to 1. It should coincide with the weak star topology. And what is a compact quantum matrix space? It's a C star algebra with this semi-norm, which is Lip norm. Okay, I written that it took 5 years to for the Rieffel to come up to a definition of the compact quantum metric space, but the definition which I have written was given in the 1999. The general definition, which is in terms of order unit space, that we'll see. And as I said, that will be a technical reason why we have to go there. But for our work, this definition works perfectly. This is a source of example. Some of the examples or most of example come from these kind of structure. In fact, the motivating example for these structures was given by the Alan Kohns in 1989. So he started with a spectral triple. What is a spectral triple? It's a yeah, just like in our previous case. In our classical case, we had the CH with the infinity norm. And we were taking one another norm on this, which was the Lip norm. Now the CX with the infinity norm is just replaced by a C-star algebra. In the C-star algebra, there is already a norm. And then we are taking what is a Lip norm, which is basically analogous of this Lipschitz norm in our case. And the Lip norm word comes from the Lipschitz word only. So let us see the motivating example which was given by Alan Kohns. So he starts with a spectral triple. A spectral triple is a C-star algebra with a representation on a Hilbert space H. And D is a densely defined unbounded operator, self-adjoint operator with a compact resolvent. And with one more condition that the norm of the A basically means the image of A looked as the operator on H. The commutator of A with the D norm should be finite whenever A is in A and in the domain of D. Then it was proved by the Alan Kohns in 1989 that the similar metric where the L of A is replaced by the norm of the commutator of A and D, this is a metric. It may not in general imply the weak star topology, but whenever it does, basically means the L is a Lip norm, then it's called what is called metric spectral triple. One of a standard example is the quantum Podol spheres, and the structure there is spectral structure there is taken to be the standard even spectral structure. The another example which motivated Rieffel was from the compact topological groups. So if G is a compact topological group with a length function, so what is a length function? It's a function from G to R plus that satisfies that Lx should be 0 if and only if Lx equal to, sorry, this is a typo, that Lx equal to 0 if and only if x equal to the identity element of G. Lxy should be less than equal to Lx plus Ly. And L should be what is called conjugacy invariant. And if we have a action of G on a C-star algebra, which is ergodic. Ergodic basically means the only invariant elements are the scalar multiple of identity. For example, the basic example, will take the compact metric space only, but assume it has a group structure. So it's a compact group which has a metric space structure also. Then G can naturally act on CG by the conjugacy action. So we are taking G with the length function also. Then in case of that group, we can see that our Lipschitz norm is nothing but given by this formula. So in general, if we have a G with a compact group with the continuous length function, and A is any unital C-star algebra, not necessarily the continuous functions on G, which has a ergodic action of G on A, then this formula will actually give us a Lip norm on A without any further condition. So these two were very basic examples and motivating examples that Rieffel started with. And for our work, I would specifically like to mention two particular examples which were given by the Bhattacharyya. So let us take the space of compact groups on any separable Hilbert space. So not just one structure, we are going to define a countably many compact quantum structures for this. So let us take K to be any natural number which is greater than 2. So for any K greater than 2, we are going to define a compact quantum structure. So what I have to define? I have to give you the Lipschitz functions and the lip norm. The Lipschitz functions are what? They are all those self-adjoint elements whose matrix entries are reals, and they satisfy this decaying condition that I plus j power k of ijth entry, the supremum of all those should be finite. And the lip norm is nothing but the supremum of this decaying condition itself, because it's finite. And it turns out that it's a lip norm. One thing I would like to mention here, I only define it on the self-adjoint element, not on the KL2. And this is why I was saying when I took the L of A star equal to L of A, that this was just a technical reason we are taking it. So we just taking on the self-adjoint element, which is a order unit space, which I'll come back again in the next two slides, that just defining on this self elements on which the state space coincide with the state space of KL2, it suffices our work.
Sorry, there's a quick question. What is KL2? Is it the space of set of compact operators?
Yeah, space of compact operators on a L2 or the separable Hilbert space.
Thanks. Yeah, go ahead.
The another example is not on any particular space, but it's a method of generating the compact quantum matrix spacing. So assume we have already a compact quantum matrix space, and B is just a C star algebra, and it's sitting inside the between the KL2 and between the KL2 and A through a exact sequence. Split means there is a splitting also sigma from A to B, which is a positive splitting. Then actually we can also give B to be the compact quantum matrix space structure, and not again one, because on KL2 there were countably many. Here also we can give countably many structure. The space of Lipschitz functions on B, which I can say vaguely, will be just take the KL2 image and take the inverse image of the lip of A under the sigma. And what will be the lip norm? It will be the L of pi of A and Lk of A minus sigma of pi of A. And it was proved by the Professor Chakrabarty that this forms a compact quantum matrix space. So these two examples by Professor Chakrabarty we are going to use in our work in the next slides. But before this, as the title of the talk says, in the quantum Gromov-Hausdorff distance, the idea of the Rieffel was not to just find a non-commutative analog of compact matrix spaces, but he also wanted to define some kind of distance between the compact quantum matrix spaces. Because between any two compact matrix spaces, we can define a distance, what is a Gromov-Hausdorff distance. I'll just recall what is a Gromov-Hausdorff distance. Assume X and Y are a subset of a compact matrix space. Then we can define the Hausdorff distance between them, which is simply the infimum of all those real numbers, so that X is sitting inside the neighborhood of Y, R neighborhood of Y, and Y is sitting inside the R neighborhood of X. What is the R neighborhood? Basically that for every X around the R ball of radius R around X, there should be an element of Y. So it is X and Y are surely compact, but they are sitting inside Z. What if we have only two compact matrix space? Can we define some kind of distance between them? Is there bigger space they are sitting inside? Surely we can take the disjoint union. On disjoint union, we can give many metric, but let us take only those metric whose restriction on X and Y are dx and dy. And now for every metric in this script m dx dy, there will be the Hausdorff distance between X and Y. Just take the infimum of those, and that is called what is called Gromov-Hausdorff distance. And it is a very, so we know that the collection of all compact matrix space is a set. So this is a very well-defined metric up to equivalence relation. What is the equivalence relation? That the Gromov-Hausdorff distance will be 0 if and only if they are isometric isomorphic. This is the motivation, okay, to define something in the non-commutative setting also, because they are isomorphic up to they are distance is 0 if and only if they are isomorphic up to the isometric isomorphic. So why not try to define some kind of distance between the compact quantum metric space where the distance will be 0. Our expectation will be that they are if and only if they are star isomorphic. Let us see how far we can reach. So if we take two compact quantum metric space, on the direct sum, we can have many Lip norms, which will, on restriction on LA and LB, they will give, on the restriction on A and B, they will induce LA and LB. Okay, with the, I would like to recall you that if we have A, LA, then the state space with this particular rho L, which was defined just like the supremum of, so rho L of some phi and psi was defined as phi of A minus psi of A, and the LA should be less than equal to 1. So this was a compact metric space. The topology was actually the weak star topology. So now SA and SB with the rho LA and rho LB, they are compact metric space, so we can define the Hausdorff distance between them. So what will be the quantum Gromov-Hausdorff distance? Just take the infimum whole those. Where L, the Lip norm on the A direction B, we are just taking which is from this script M, LAB and LB. Now, what was your expectation that this should be a proper metric? Up to some equivalence class, we were expecting that distance of QAB equal to 0 if and only if A and B are star isomorphic. That would be our expectation, but it doesn't turn out. What turned out is that the distance is 0 if and only if they are order isomorphic on the self-adjoint part. So that was the case when on the KL2 I was just working on the self-adjoint matrices only. And this is why you even took Rieffel 5 years to come up to a proper definition, and the final definition is in terms of order unit spaces. And the definition which we are taking, that gives a particular example of this. But as I said, for our work, it suffices. And this was also a technical region, which I mentioned in the beginning, but it also gives us some flexibility because not just the C-star algebra, we can even talk about some kind of quantum structures on the order unit space. So having said this, now I'm going to combine all this work which we have seen till now, and we are going to see a particular kind of sequence, the Toeplitz algebra on generalized Bergman space, and we'll prove that it converges. We'll actually state that it converges to the, we'll see some result that it converges to the odd spheres, which basically means the space of continuous functions on odd spheres in this particular convergence, which is quantum Gromov-Hausdorff convergence. So let me start with some notations. Let D be any natural number. Let B2D be the open unit ball in CD. Then we can define a volume measure on B2D. In fact, for any D, n greater than equal to D, we can define volume measures, which are given by this formula 1 minus mod z square n minus d dv. And what is Cn? It's just a normalizing constant, so that this dvn is a probability measure. And what is the use of this 1 minus mod z square n minus d? Because let us consider this space, which is called generalized Bergman space, the space of analytic functions which are square integrable with respect to this dvn. Then this is a inner product space with respect to the inner product, usual inner product in L2. But this is a reproducing kernel Hilbert space with respect to this kernel function. And here it's basically coming because of the factor of 1 minus mod z square n minus d we took above. For n equal to d, it's called Bergman space. And for n greater than equal to d, it's called generalized Bergman space. On these spaces, we can define Toeplitz operators. What are Toeplitz operator? That if we take any continuous functions on the closed unit ball, then we can define a function from h to n, which is basically the multiplication of each function by phi. But the problem is that by multiplying by the multiplication function, we might go out of hn. It will be just L2 function. It may not remain analytic, but let's just project it back. through our usual orthogonal projection. So this is what are called Toeplitz operators. And what are Toeplitz algebra? These are C-star algebra generated by these. The Toeplitz algebra elements are actually not too far from the Toeplitz operators. In fact, for Bergman space, when n equal to d, it's well known that any element of the Toeplitz algebra is just a Toeplitz operator and the addition by a compact operator. In fact, under the quotient, it's isomorphic to the continuous function to the boundary of the closed unit ball, which is nothing but the circle of dimension 2d minus 1. And the isomorphism is usual isomorphism, just take phi and restrict it on the boundary. So this case is for the Bergman space, but all the generalized Bergman space are separable Hilbert space. Using the isomorphism with the HD and some basic result from the C-star algebra theory, we can prove that it's hold for any HN. Basically, there is a, I should say, short exact sequence from KHN to the CS2D and minus 1 between the Toeplitz algebra comes between. So it suddenly reminds us of the example 2 of the Professor Chakravarti. The only problem is it splitting by a positive splitting. In fact, there can be many splitting. I'll show you one, which is basically take, so I'm taking sigma, take any function on the boundary and extend it to the whole closed unit ball by the unique solution of Dirichlet problem. Whenever the function on the boundary is positive, the unique solution of the Dirichlet problem has to be positive. So we have got a splitting. Now on KHN, we know a lot of compact quantum matrix space structures. On the continuous functions, because the circle of dimension 2D and 2D minus 1 is a compact space, there is already non-compact quantum matrix space, which was given by the Lipschitz functions. And the sequence is splitting. So we can define a lip norm on the tau n. What are the first C? So on KHN, we can take countably many, but for countably many structures. But for fix n, I'm going to fix one structure. So this is the same structure which was in the Professor Chakravarti example 1. So there we had the decaying condition I plus j power k. So here I'm taking k to be particularly n plus 2. Why I'm taking plus 2? Because k was greater than 2. N can be 1 also. So we are making sure that n plus 2 is always greater than 2. Then the tau n will have this compact quantum structure. Basically, the lip of KHN directs with the Toeplitz operator generated by the real Lipschitz functions and taking the solution on the Dirichlet problem. Yeah. No, it's not different. What we have done, we found this split exact sequence, and now on tau when we are going to define something. Yeah.
Also had compact quantum group structure, but compact quantum matrix space structure on only the compact operators. By this we have on the Toeplitz algebra.
So it's basically given by the direct sum of the Lipschitz function on KH and on the Lipschitz functions on the circle, and the lip norm is basically given by this. So this structure basically comes only from the Professor Chakravarti paper. But what is the interesting? Let me state our main result as the announcement that this sequence of the compact quantum matrix space which we have got, that actually converges to the continuous functions on S2D minus 1 in the quantum Gromov-Hausdorff distance. So this is the new work. Defining the structure was okay. That was also new, but that came from the previous papers. But this is some new work. And yeah, I'll end my talk here with the references. The first paper is by the Professor Chakrabarti. The second paper is where the Toeplitz operators on generalized Bergman space are generalized, and we use those results to find that split exact sequence. The third paper is basically a kind of survey article, which Rieffel wrote in 2004 after he was sure what kind of definition he wanted to take for the compact quantum matrix space. The fourth paper is where the quantum Gromov-Hausdorff distance is defined. And the last paper is actually the application of all these work in in string theory. So in string theory, people talk about something called matrix algebra converging to the sphere, where the sphere means the two sphere. So that was actually one of the motivation of Rieffel also, and he found out what was that convergence. Yeah, so now I'll end my talk here and wait for your questions or comments.
Thank you. Any questions for Sushil?
Is there a reason to
Only for?
look at only the Bergman space over the ball? Like, Toeplitz, the Sitter algebra generated by Toeplitz operators that are well studied, right? So as long as you have compact operators sitting inside, you should be able to push this through, right?
Yes.
Yeah.
It need not be special to the ball.
Uh,
Ball is what we did, but it's likely to hold in more general domains. They're even pretty general actually, strongly superficial domains. The moment you have Bergman spaces. But a sequence of Bergman spaces. So you need a sequence of Toeplitz algebras converting into
So you need the weights.
weights.
That's the Bergman covering.
Yes. Yes. That's just the power of the Bergman pattern.
Any questions from online audience?
What about, I mean, holomorphic sections of line bundles on scalar manifold? That'd be an interesting thing to look at.
We haven't gone in that direction. At the moment, we have found this result. Yeah, but these results can be
Because you
generated.
can, I mean, if you have an ample line bundle, you can sort of take powers of that. And I don't know if, as you take higher and higher powers, I mean, that perhaps can be an analog of your sequence Tn. I mean, I don't know. So maybe that might.
Yeah, we'll try to see what if something can be done in that direction.
Okay, any further question? Not, let's thanks for it again.